We will now discuss the existence of hedging portfolios and the completeness of market models. Just a reminder about the Ito representation theorem. If we have a Brownian motion on a probability space omega fp with a filtration that is generated by that Brownian motion, augmented to satisfy the usual conditions, and if x is a square integrable ft measurable random variable, then there exists a unique predictable process h such that x can be expressed as its expectation plus the stochastic integral of h. From that, it is easy to obtain the martingale representation theorem, which says that every martingale with respect to the filtration generated by a Brownian motion is essentially a stochastic integral with respect to that Brownian motion. We'll see now that the existence of hedging portfolios is connected to the structure of the volatility matrix, as for that matter is the existence of a risk-neutral measure. So I'd like to remind you of some linear algebra first. Suppose that A is an n by k matrix, which will be the volatility matrix later. Then A has linearly independent columns, if and only if whenever A times x is equal to the zero vector, then x is equal to the zero vector. Recall that A times x is simply a linear combination of the columns of A with coefficients equal to the components of x. And thus to say that A times x is equal to 0 is to say that a linear combination of the columns of A is equal to 0, and that can only be the case if the coefficients are 0 when the columns are linearly independent, and vice versa. Now recall that a square matrix is invertible if and only if it is full rank. Thus if B is a square matrix, then B is invertible if and only if whenever B times x is equal to 0, it is the case that x is equal to 0. Now suppose that our n by k matrix A has linearly independent columns. Then B, defined to be A transpose times A, is a k by k matrix and therefore square. Now if B times x is equal to 0, then A transpose A times x is equal to 0, the 0 vector. So if we pre-multiply that by x transpose, we will get 0, a number. And if you look at this expression here, you see that it is precisely the dot product of ax with itself. In other words, it's the square of the norm of ax. Thus, the norm of a times x is equal to 0, which means that a times x is equal to the 0 vector, and that implies that x is equal to 0, as we've seen in the first point here. In particular, if A has linearly independent columns, then the square matrix A transpose A is invertible. In that case, the inverse of A transpose A multiplied by A transpose is a left inverse of A, because clearly if we multiply this by A over here, we will get the identity matrix. Conversely, if A has a left inverse C, then whenever A times x is equal to 0, also C times A times x is equal to 0, but C times A is the identity matrix, and thus x is equal to 0, and so A has linearly independent columns. Thus we see that a matrix has linearly independent columns if and only if it has a left inverse. In the same way, one can prove, using transposes for example, that a matrix A has a right inverse if and only if it has linearly independent rows. Let's now consider the existence of hedging portfolios for European-style contingent claims. Let Q be a risk-neutral measure, and suppose that X is a European-style claim with payoff X capital T at expiry capital T. To replicate this claim, we need a portfolio of theta such that the discounted terminal value of X, in other words the discounted payoff, is equal to the discounted terminal value of the portfolio, which is just the initial value plus the discounted gain. Now we can turn the discounted payoff x bar t into a martingale in the usual way, simply by taking conditional expectations. In other words, we define a martingale M to be the Q conditional expectation of the discounted payoff with respect to the sigma algebra Ft. By the martingale representation theorem, that martingale can then be represented as a stochastic integral. In other words, there is a predictable process H such that the discounted payoff is equal to the Q expectation of the discounted payoff plus a stochastic integral. If we now compare these two equations, it's clear that what we require is that theta transpose times ds is equal to h transpose times dw. Now theta times ds is just theta times the diagonal of S times the volatility matrix dw. And so what we require is that this expression here is equal to H transpose, which if we take transposes implies that sigma transpose times diagonal S times theta is equal to H. We have to solve this for theta. And this system will have a solution for every H if and only if every H lies in the column space of the matrix sigma transpose times diagonal S. Since the diagonal matrix is invertible, it follows that this system has a solution for every H if and only if the column rank of sigma transpose is K. Now, since the rank of sigma transpose is equal to the rank of sigma, this implies that the rank of sigma is equal to K, and as sigma is n by K, it follows that the columns of sigma must be linearly independent. It follows also that K must be less than or equal to n, because the rank of sigma is less than or equal to K and n. Now, if the columns of the matrix sigma are linearly independent, then it will have a left inverse, which as we know can be expressed as follows. Define now theta transpose to be H transpose times the left inverse of sigma times the inverse of the diagonal matrix, i.e. define the risky parts of the components of the portfolio theta as follows. Also choose the bank account component of theta to make theta self-financing with an initial value equal to the Q expectation of the discounted payoff. In that case, the discounted terminal value of the portfolio is just equal to its initial value plus the discounted gain. By definition of theta 0, the initial value of the portfolio is just this expectation here. And of course, the gain is just this stochastic integral. If we now replace theta by the way we've defined it here, and we also replace ds bar by the dynamics in the generalized Black-Scholes model, we see that the discounted terminal value of the portfolio has a stochastic integral component that looks like this. This part here is the portfolio theta transpose, and this part here is ds bar. Then we see that the two diagonal matrices here multiply out to the identity matrix, and then that the left inverse of sigma multiplied with sigma also multiplies out to the identity matrix, and so that we're just left with H transpose. Hence we obtain the following expression, which is just equal to the discounted payoff of the claim X by choice of the process H. In other words, theta is a replicating portfolio for X. Hence, if the rank of sigma is equal to K, i.e. if sigma has a left inverse, then any contingent claim is attainable. In other words, our market model is complete. Let's now consider the sweet spot for modeling in a generalized Black-Scholes framework. Consider a generalized Black-Scholes model with n risky assets and k sources of noise. Firstly, to find a risk-neutral measure, we have to find a Kirsanov kernel, in other words, a solution lambda to the linear system sigma times lambda is equal to mu minus r. Here lambda has the same dimension as the Brownian motion, in other words capital K, and sigma is an n by k matrix, and thus we have n equations in k unknowns. Heuristically speaking, we expect such a system to have a solution when the number of unknowns exceeds the number of equations, in other words when k is greater or equal to n. If k is strictly greater than n, we expect there to be infinitely many solutions. Secondly, to replicate an arbitrary claim X, we require a portfolio theta satisfying the following equation. In this case, the unknown is the vector theta consisting of the risky asset components. In other words, at each time t, we have to solve a linear system of equations that looks like this for the risky components, and so we have k equations in n unknowns. Thus, again, heuristically speaking, we expect a solution to exist if the number of unknowns exceeds the number of equations, in other words, when n is greater or equal to k. If n is strictly greater than k, we expect infinitely many solutions to exist. Thus, if k is strictly less than n, we expect to be able to hedge every contingent claim, but in more than one way because we expect infinitely many solutions to exist. Those hedges might not all have the same initial cost, and therefore there might be arbitrage, although market forces ought to prevent this. If k is strictly greater than n, on the other hand, we expect to be able to solve for lambda in many ways, and therefore we expect that there will be many risk-neutral measures, and that there will be contingent claims that we cannot replicate. The sweet spot, therefore, is where k is equal to n and where sigma is invertible. Then we will have a unique risk-neutral measure and a complete arbitrage-free securities market model. Saying, heuristically speaking, we expect a solution to exist is maybe a bit imprecise, so here is another way to see this. Firstly, for a model to be arbitrage-free, we require that there exists a risk-neutral measure. In other words, we require that there is a solution to the system sigma lambda is equal to mu minus r. Such a solution will exist if the vector on the right here, mu minus r, is in the column space of the matrix sigma, and it will exist for any choice of mu and r if the column rank of sigma is n, which implies that the rows of sigma are linearly independent, that n is less than or equal to k, and that sigma has a right inverse. For if sigma has a right inverse, sigma r inverse, then if we define lambda to be the right inverse times mu minus r, we see that lambda will solve this system. Now, for sigma to have a right inverse, its rows must be linearly independent. In other words, its rank must be equal to n. In that case, one right inverse can be defined as follows, as you can easily verify. In order for a model to be complete, on the other hand, we saw that we require sigma to have a left inverse, in which case one left inverse is given as follows. For sigma to have a left inverse, its columns must be linearly independent. In other words, the rank of sigma must be equal to k. And thus, in this case, we require that k is less than or equal to n. In other words, for a model to be complete and arbitrage-free, we require that k is equal to n and that sigma is invertible. Notice that this is a modeling decision. You are modeling a certain number of assets, you get to decide the number of Brownian motions required, and you get to specify the volatility matrix. Notice that no arbitrage and completeness of a model pull in opposite directions. If a model is overly complete, there might be claims that can be hedged in many different ways, and not all of those replicating portfolios might have the same initial price, violating the law of one price and therefore no arbitrage. On the other hand, if a model has few securities and many sources of noise, then very few contingent claims can be replicated, and there will be many risk-neutral measures.